Christians in Science is a network of scientists who share a Christian faith, and we are members of the Evangelical Alliance. Our aim is to promote biblical Christian views on the nature and scope of science and how it interacts with the Christian faith. We also want to encourage those engaged in scientific work to maintain an active faith. We would like to work with and support your church as a partner in mission by providing you with resources to enhance faith and worship within your church and to assist you in your outreach to the local community. Affiliated churches enjoy the benefits of providing you with guidance and advice about putting on science and faith-based events. This could include children, youth and family events, or a series of topics for your church services or home groups. We can provide you with highly qualified and distinguished speakers on a range of science and faith topics, and you will also receive regular communications from CIS about our national and local events. We encourage affiliated churches to support the work of Christians in Science by prayer and regular financial donations towards our continued work across the UK. To find out more about our aims and how to become an affiliated church, please visit the Christians in Science website.
The Big Bang is an opportunity for children and young people to think about the ways that science and faith and more broadly philosophical questions might come together to create some surprising results.
I enjoy bringing the children to this event every year. It gives them a chance to pause, take a breath in their busy schedule, their busy lives, move their head away from the computer screens, and gives them time to think and consider the things that are important in life. And they hear from a range of experts and get a chance to pose questions that they've perhaps even never thought of before.
Today to find out how I can teach evolution and inheritance in a way that's sensitive to the Christian ethos of our school and also to be true to the science curriculum. I find that when I start teaching this topic, in the past I've set it up as Christians believe this but scientists say this, and I'm aware that I'm already setting up as opposing views. So it'll be interesting to find out how I can teach this in a way that doesn't pit one side against each other.
Good afternoon, everyone, and welcome back to the final part of our Christians in Science conference on digital theology and the church, or indeed welcome in general if this is the first part of the conference you have been able to join us for. And we have three further talks for you this afternoon, which all in their own ways deal with aspects of the future of what we might want to call the digital revolution. But as we've already been challenged on earlier today, can we even call it that? The first of our talks will be the annual Christians in Science Oliver Barclay lecture, which is given this year by Dr. Anna Pearson. Following Anna's talk, we will then have two more talks that I expect to particularly challenge and provoke us, looking more directly at the role of digital technologies in the future shape of society and of the church as well. At the end of each talk, there is, as usual, a period for asking questions to our speakers. Please submit those at the end of each talk, either through the comments box on YouTube or by sending them to steph.cis@outlook.com. And we will do our very best to get through as many of these as we can. We also have a feedback form for this conference, the link to which you should be seeing in the comments box. If you could fill that in at the end of the conference, it would be greatly appreciated. We'll also email it out to you all in case you don't get a chance right now. So without too much further ado, let's dive into the first of our 3 talks this afternoon, the annual Oliver Berkeley Lecture, which is named appropriately in honor of Oliver Berkeley, who was one of, if not the founder of Christians in Science, or rather the Research Scientist Christian Fellowship, as it was known at the time. He was also a significant presence in the UK evangelical church in the mid to late parts of the 20th century. This lecture provides an opportunity for someone from the next generation of speakers in the field of science and Christian faith to speak on a topic of their own choosing at all of our major conferences. This year, our speaker, Anna, has chosen to speak under the title Quantum Mechanics, Faith and Unresolved Questions. This might at first glance seem to be giving you a bit of a breather from our theme of digital theology, but we should keep in mind that all of the technologies and opportunities that we are talking about today rely on the very fundamental physics of the quantum world in which to work. Indeed, as technology behind our devices becomes ever smaller to make them ever faster, the greater the role that quantum mechanics begins to play in them. This can create operational challenges, but also offers new routes for innovation, and so new devices. Having long been fascinated by quantum mechanics, our speaker completed a DPhil and a postdoc in quantum information thermodynamics at the University of Oxford, and she currently works on the quantum natural language processing team at Cambridge Quantum Computing. And so with a resume like that, she is very well prepared to bring us her lecture on quantum mechanics, faith, and unresolved questions. Anna, over to you.
Good afternoon, and thank you for joining my talk on quantum mechanics, faith, and unresolved questions. Quantum mechanics is a subject which has fascinated me since I first learned about it as an 18-year-old, and I'm excited to share some of these ideas with you during my talk. So to give you a brief outline of the talk, I'll first give a short introduction to the quantum realm, recapping the properties of waves, outlining the double slit experiment, and then looking at superposition, observation, and other phenomena. We'll then look at a few of the unresolved questions within quantum mechanics, think about some unresolved questions within faith, and then finish with discussing living with mystery. Before we go any further, though, I'd just like to give this warning from Richard Feynman that I think I can safely say that nobody understands quantum mechanics. So when I first learned about these ideas, I couldn't sleep at night, and I had to change my application to study physics at university because I simply had to find out more. So let's have a think about waves. If you look at the left-hand side of your screen, the bottom 2 waves, you'll see 2 waves that are in phase, which basically means the squiggles line up with each other. If you add them together, you get the top wave, the thicker line, which gives you a wave which has twice the amplitude. So if it's a light wave, it's going to be brighter. If it's a sound wave, it's going to be louder. And this is known as being in phase, or also known as constructive interference. However, if you look at the right-hand side of your screen, the 2 waves are out of phase. You can see the squiggly lines don't line up. And when you add these waves together, you just get the straight line at the top. This is also known as destructive interference. So if it was a light wave, you wouldn't see anything. If it was a sound wave, you wouldn't hear anything. And this is important for the double slit experiment. So the setup is as follows. You have your source. In this case, it's an electron being gone, but the source can be whatever you want it to be. You pass it through a double slit, and then you have a screen on the other side of the double slit to record the outcome of your experiment. Now, if you imagine particles, you might think that there's something like footballs or stones or something like that. And you might expect that if you pass them through a double slit and they hit a wall on the other side, you would just get 2 lines which show which slit the particles pass through. However, if we do this experiment with electrons, so this is data from the Hitachi lab, which can be found online here. So what you can see, the bright spots appearing are single electrons, which have been passed through what is basically a double slit. And at the moment, you can't see any pattern, but as we watch this video, we're going to see a pattern building up. An important point to make about this experiment is that it's one electron passing through the slits at any one time. So if we get any interference, which we will see at the end, it can't be an electron interfering with another electron. It has to be interfering with itself. I'll just speed up a bit. And so what we begin to see, instead of the pattern that you might expect from particles which behave like stones or something, we actually get an interference pattern. So the interference pattern is the bright fringes in the middle, and with fringes on either side, which are also bright, with dark fringes in between. And this is the signature of waves. And here we can see it outlined on the schematic. So we have the electron being done, which has fired the electrons through the double slit, and on the screen, we get the interference pattern. It can be easier to visualize if we imagine that waves have passed through the double slit. And here you can see the bright fringes where we have constructive interference, and the dark fringes where there's destructive interference. And so to explain this behavior of electrons, we use the term wave-particle duality. So in some sense, they behave like waves because we get an interference pattern. But in another sense, they behave like particles because they arrive on the screen in one location, like a particle would. And this is at the heart of quantum mechanics, the idea that an object can have wave-like properties and particle-like properties. So just to recap everything I've just said, we have this animation. And this is an artist's depiction of what might be going on, because obviously we can't actually see quantum particles. So here we have what you would expect if you just fire particles through, or footballs or stones or anything that you think would be a rigid body. And there's no interference pattern. And then if we send a wave through, you can see that as the wave reaches the slits and passes through, on the other side it begins to feel with the part of the wave which went through the opposite slit, and the interference pattern builds up on the screen. Now with a quantum object, and I will stress this is the artist's depiction, they imagine it behaving like a wave as it goes through the slits, and then like a particle as it hits the wall. So this experiment also has the principle of superposition, because you have the particle or the quantum object existing in both slits at the same time. And that gives rise to an interference pattern. And then one thing I haven't covered yet is the effect of observation. And the effect of observation actually changes the outcome of quantum experiments, which is another difference which makes it vastly different to the classical realm. So with the observation, the quantum particle no longer passes through both slits, it only passes through one slit, and the interference pattern is entirely washed out. So this animation is freely available on the website Tutors Quantique, which will appear in a minute, and I would highly recommend this website because there's lots of other animations about quantum phenomena. So we've covered the idea of wave-particle duality, superposition, so that is the object existing in both slits at the same time, although this principle can also be extended to other things, such as quantum objects have a property called spin, and if the spin is in a superposition, it can be pointing up and pointing down at the same time. And we've also talked about observation, so the idea that when you are observing something, you somehow change what's happening. This is very, very different to our normal classical science. I'd like to cover 4 more things. So we have entanglement, quantum tunneling, indefinite causal order, and the fragility of quantum information, or known as the no-cloning theorem. So let's start with entanglement. So the principle of entanglement means that if you have 2 quantum particles and they are entangled, you can separate them by a vast, vast distance. And say it's an entanglement and you measure the spin property and you find that the spin is spin down in the one particle. Instantaneously, the other particle will be spin up. And it doesn't really matter how far they're separated. So once they become entangled, you can't consider the system as 2 separate systems. You have to consider it as one whole system, no matter the distance. Quantum tunneling always makes me smile. So what you see here, the black line is an energy landscape and the object's in green. Now, classically, the object needs to get more energy to get over the hill. It's just like when we're out walking and we want to walk up a mountain, we need some energy to get up the hill. However, quantum mechanically, it doesn't actually need to have enough energy to get over the hill. It can just tunnel straight through to the other side. And this is used in fusion inside stars and also in the scanning tunneling microscope. Now, indefinite causal order. So if we think of superposition, and we've discussed it with respect to position, so the object being in slit A and slit B at the same time, or I also mentioned it could be with spin, so it could be spin up and spin down. Or another thing is that it could be with the energetic state of an atom, it can be decayed and not decayed. However, this can be extended to the order of events. So if you look at section A here, we have a picture of two people, normally known as Alice and Bob in the quantum community. And let's say that Alice performs an operation and Bob performs an operation. And the path in section A is that first Alice performs the operation and then Bob performs the operation. And then in section B, we have Bob performing an operation and then afterwards Alice performing an operation. However, if you apply the superposition principle to the causal order of events, you can get panel C. So you can get the path that in time being Alice then Bob, but it can also simultaneously be Bob then Alice. And this is known as indefinite causal order. I've been thinking a bit about this with a theologian, Emily Qureshi-Hurst, and we have a paper that has come out in Zigen very recently. So if you're interested, please take a look at that. And then the no cloning theorem. So just to explain the sheep, it's Dolly, well, it's not actually Dolly the sheep, but it should represent Dolly the sheep. So classically, we can clone things. However, quantum mechanically, a quantum state cannot be cloned, and this is known as the no cloning theorem. Again, this is very, very different to our classical intuition. And if we think about the consequence of this, this is from It Keeps Me Seeking, the invitation from Science, Philosophy and Religion. We don't know if brain function depends on the details of the quantum states. But if they did, then it may be that the type of copying process sometimes invoked by science fiction writers, where they imagine that people could one day save backup copies of themselves, may be physically impossible. So this has bearings on human identity. So if quantum states do make up part of our brain and part of our consciousness, and this is an open question, then maybe that's physical evidence that we are unique. Although as Christians, I think we would say that every person is unique anyway. But it may be that science also says this, but this is an open question. And so I've just mentioned an unresolved question if quantum mechanics has bearings on consciousness, but there are many unresolved questions in the quantum community. So I've just picked a few from a survey that was taken at a conference of quantum physicists and philosophers. And just to give you a flavor of the discussion that's going on. So the first question is, what is your opinion about the randomness of individual quantum events, such as the decay of a radioactive atom, or it could be the path that the electron chooses when it's observed. So if it goes in the right slit or the left slit, that seems to be entirely random. Oh, I should note that the percentages add up to more than 100% because the participants were allowed to tick more than one box to answer the question. And so, yeah, so there's this debate going on about if randomness is irreducible, if it's a fundamental concept, or if it's only apparent. And there's no consensus yet. Question 2 is one that you wouldn't even think to ask when dealing with a classical system. And that is, do you believe that physical objects have their properties well defined prior to and independent of measurement? And the participants in this case are almost 50-50 between yes in some cases and no. And then the last question I'd like to present to you is the question about superpositions of macroscopically distinct states. This is just, is it possible to get a superposition of a larger object, a macroscopic object, as opposed to a microscopic object? And this leads on to the paradox of Schrödinger's cat, which was on the title page, which some of you may be familiar with, but for those of you who aren't, I'll just recap it quickly. The idea is, if you have a radioactive atom and it's in a box, and in the box you also have a lever, a hammer, a vial of poison, and a cat that is alive, at least to start with, and the box is closed. Now, when the atom is not being observed, we know that it can be in a superposition of being decayed and not decayed. And this atom is linked to the lever in such a way so that when it decays, the lever will drop and the hammer will smash the vial of poison, filling the box with poison and killing the cat. But the question is, before observation, while the atom is in the superposition, does the superposition extend to the hammer being fallen and not fallen, and the poison being in the vial and out of the vial once it's been broken? And can the cat therefore be dead and alive at the same time before the box is opened? Now, if you think about this, it doesn't really sit well with you, because the idea of a cat being dead and alive sounds like something from a horror movie rather than real life. And so it's a paradox. And so scientists are trying to find out if there's a boundary to the quantum realm. So maybe the quantum mechanics can apply to the atom, but maybe not to the cat. I mean, some will say it could, some would say it couldn't. And so they're carrying out experiments to try to find out where this boundary lies, if it exists. Some people would say it doesn't exist. And so in 2011 and then later on in 2013, they did the double slit experiment that we looked at earlier, but with these molecules. So with molecules of up to 430 atoms in the first one, and then 2 years later, they managed to double the size of the molecules. So they had over 800 atoms existing in 2 slits at the same time. And then if you go to even large objects, you have this little, it's called a mechanical resonator. So it's just a little aluminium drum of the order of 10 micrometers. And in the past few years, they've managed to entangle 2 of these mechanical resonators. So you have quantum behavior in a system that is of the order of 10 micrometers. So we haven't reached the size of cats yet, but the boundary is being pushed further and further experimentally. And I'm particularly interested in this question about the boundary of the quantum realm, and I've been looking at in my PhD the question of gravity. So what about gravity? I should mention my supervisors have been Professor Andrew Briggs and Dr. Natalia Ares, and we've worked with some theorists, and they've said, let's consider gravity being classical rather than quantum. And they've predicted 2 effects. So the first one is, when the object becomes massive enough, it can't exist in a superposition. So you couldn't have it existing in 2 places at once. And then the second effect from their model is that the gravitational interactions within the object will cause it to self-heat. And this hasn't been verified experimentally yet, and you can read the details in the reference at the bottom there. And so we've set up an experiment to test for the second of these effects, the heating effect. And so we take a little silicon nitride membrane that's about 1 millimeter by 1 millimeter and 50 nanometers thick, and we put it inside an aluminium box, which you can see in the bottom left-hand corner. We then put the system in a dilution refrigerator. So here you can see a picture of the lab. So those big grey tubes are dilution refrigerators, and they can reach temperatures of around 10 to 20 millikelvin, which is very, very, very cold, colder than space. And then we send in microwaves into the box, or the cavity as it's called, and we read out the microwaves after they've interacted with the system, and we get a peak, as an example in the bottom right hand corner. And the area of that peak allows us to calculate the temperature of the membrane. And so we want to do this at many different temperatures and see if the membrane is at the temperature of the environment, or if it is very slightly hotter due to the gravitational interactions. So we've done one run of this experiment, but can't draw any conclusions from it. But we're hoping to run it again in the near future. So it's work in progress. So that's been quite a lot of science and some unresolved questions. But how does this relate to faith? So often when thinking about science and faith, at least personally, I think about how my faith inspires my science and how I get inspiration from the Bible and from nature, that I want to study the world that I believe God made. But more recently, I've been thinking about how my science can actually help my faith, specifically when thinking about unresolved questions. So, for example, prayer. Prayer is something I believe in. I pray myself. I have friends who pray. I pray for friends. Friends pray for me. But I couldn't explain to you how it works. Just like I investigate quantum mechanics without fully understanding it, I won't say I investigate prayer, but I can engage with prayer without fully understanding it. The same goes for the Trinity. I can't understand the Trinity. It's beyond my comprehension, but I can still place trust in a God who reveals himself as a triune God. And part of me likes the idea that he is beyond my understanding, that the creator of the universe is bigger than my mind can grasp. And also, if I can't yet fully understand nature, maybe never will fully understand nature, should I expect to fully understand the one who I believe is behind nature? And as a last example, we have the topic of suffering, which is perhaps the most sensitive and difficult topic to broach, both on a personal level and a societal level. I find this a difficult topic as it moves beyond an issue that I can wrestle with in my head to one that affects my heart as well. It's not simply an intellectual issue, but an emotional one too. Perhaps for this example, it feels rather trite to say that I learned from my approach to science to help me with my faith to cope with suffering. When dealing with this issue, I remember that there are things beyond what I can understand in this world, but I also remember that there is one who understands, who entered this world of suffering and partook in it, who's there to comfort and sustain, even when we can lose sight of it. And so how do we live with mystery? How do we live with unresolved questions? Both quantum mechanics and faith present us with questions that currently have not been fully resolved, and some may not be resolved within our lifetimes. But the approach one can take when facing quantum mechanics can be of help when facing difficult issues in faith, to be humble, to acknowledge the limits of our own understanding, but to refuse to give up the grasp, the search for more comprehensive grasp. I really, really like the fact that the Anglican liturgy uses the phrase, "Great is the mystery of faith." The idea of faith being a mystery is not a new one. And a verse that I come back to when the questions can get a bit much is this one in 1 Corinthians. "For now we see only a reflection as in a mirror, then we shall see face to face. Now I know in part, then I shall know fully, even as I am fully known." One day we will have all the answers. And while we don't, we can rest in the knowledge that somebody does. Thank you for listening to my talk, and I'm really looking forward to your questions and for discussion on this topic.
Thank you very much for your lecture, Anna. You certainly covered quite a lot of ground there, and your passion for and your knowledge of the subject were both extremely clear. Certainly some mind-blowing concepts in there, so I'm sure they'll have raised some good questions. They're starting to come in already. Just to say, I can also second Anna's recommendation of her paper in Zygon, exploring the theological consequences of the ordering of quantum events. It's certainly not a topic I had considered from a theological perspective before. It was really interesting stuff. So just to get us going on the questions, has there been any further progress in your experiments with the gravity influences on quantum events since you prepared this talk? Or do you anticipate much more work there?
Well, there's certainly more work to be done, but as my postdoc was a short-term contract, so I now work in a quantum computing company, so I haven't done any more work on that particular experiment, but I hope somebody will. So yeah, there's certainly questions to be answered there.
Excellent. Yeah, it sounded really interesting, and it's great to see kind of a testable model of a quantum effect. So another question coming in. So in talking about observation, we can be talking about an interaction on the macroscopic scale with an entity, or we can be talking about its perception by a human brain. Do we need to distinguish between these types of observations?
Yeah, that's a good question. Good question, and we do need to distinguish. So when I was talking about observation, I was trying to leave humans out of the picture. So observation means the information is accessible, but not necessarily that a human has accessed it. So with the double slit, the observation is when you put the detectors in the slits and the information is recorded by the detector. But you don't need a human reading off what the detector recorded for the observation to have happened. The observation happens when the electron is detected independently of humans. But yeah, we do need to distinguish what we mean when we talk about observation. And then there's a debate about, does quantum observation depend on consciousness? And there's a whole can of worms to be opened there.
Yeah, it's a very big can of worms.
Yeah.
Another question. How can we tell? Oh, sorry, reading the same question. I think. No, I'm not. That was a bit uncertain for me. So how can we tell the difference between an observed event and a non-observed event? If an event is not observed, then one would not have any empirical data to compare it with.
Again, so another great question. So when we're talking about an observed event and a non-observed event, as the questioner rightly points out, you don't observe a non-observed event. But what you can observe is a footprint of what happened. So if we go back to the double slit, when you send the particles or the electrons through without observation, you don't observe what happens when they go through the slit, but you observe the footprint they leave on the screen. And then you put the detectors there. This time it is directly being observed which slit it passes through. And again, you look at the footprint that is left after the event, and it's an entirely different footprint. So the observation takes away the interference pattern. So the interference pattern is the footprint of the particle being in a superposition when it's not observed, if that makes sense.
Yeah. As much as it will do in quantum mechanics. Can you say something about the idea of entanglement and incarnation? Moving a little bit away from pure science.
That one. It's not. I haven't thought about entanglement and incarnation, but I'll put it on my list of things to think about. Yeah, I'd probably need a bit more feedback from the person asking the question, but I don't think I have anything to say on that. Sorry.
We'll give them a chance to say something more while we ask a few more questions. If they were ever resolved in the here and now rather than waiting for a new creation, for example, would you miss the mystery that is in quantum mechanics and or Christian faith? How important to you is it that mystery is present?
So I don't think I would miss the mystery, because the whole point in doing research is to understand the mystery. So you take the mysterious out of the non-understood concept. So I think if we could solve the mystery of quantum mechanics, it would be like part of something I hope to achieve in my lifetime, or that I hope humanity will achieve during my lifetime, that we will solve some of the mystery in quantum mechanics. And then I would love to understand and be completely sure about everything in faith, but I think I'm more confident that the mystery will be solved in quantum mechanics than the mystery will be solved in faith. But I think, I just come back to that verse in Corinthians that like now we know in part, and one day we will know fully, even as we are fully known.
Would you say that faith in some ways reflects a kind of quantum reality? That they both have mystery as maybe a unifying concept in them?
Yeah, they both have mystery which unifies them, but I think a quantum reality is part of the physical world. I mean, we have quantum mechanics that's about as far as we've got. I mean, there might be post-quantum mechanics, but we haven't got there yet. Whereas faith, I think faith is much bigger than quantum. Faith encapsulates all of life, all of the universe, all of our being, whereas quantum is limited to a study of the physical world. So I wouldn't want to map faith directly onto quantum.
Yeah. So you mentioned about being interested in the quantum world and how it led you to be inspired to kind of study it more. Your faith led you to be inspired more. Is there anything particular from your learnings in quantum physics that's changed a theological concept or model for yourself?
Well, if I think back to like when I was a teenager, I was very, very sure of things, and I guess you take the verse kind of faith as being certain of what you don't know, and I was very sure of things. Things were very black and white for me. And then the more I studied science, the more I realized there's an awful lot I didn't know. There's an awful lot that humanity doesn't know, and there's an awful lot we don't know when we'll ever know it at all. And so I think studying the quantum world impacted my faith journey in that it made me more comfortable with things not being black and white, and things being mysterious, as I know I've used that word a lot, and things being a bit uncertain. And it just helped me be okay with that in my faith and in the wider aspects of life. So that's how it helped me.
Do you have any advice for young people, maybe in their A-levels, who are studying sciences, who may be told that there is a conflict between science and faith? How have you made that journey yourself?
Yeah, so I actually grew up thinking that the world was created in 6 days, and I had a big problem with evolution. And I think my advice would be look into the resources that are out there, listen to the people who are very qualified to speak on these issues. So when it came to evolution, I read Dennis Alexander's book about creation or evolution, do we have to choose? And I had to think about it for about 6 months, but then I realized that, evolution and the idea of a God who made the world are not in conflict. So for me, it was a gradual journey of being exposed to the ideas that are out there, and that I would just encourage you that science and faith are not in conflict. If you're Christian, you believe God is behind the world, he made the world, but I think he also wants us to study it, and he also wants us to learn more about it. So I just want to encourage you that you might have to change some ideas if you have like preconceived set ideas, but they're not in conflict, and it's a marvelous world to be discovered. So go do that science degree, get stuck in, go for it.
Well, I entirely agree with everything you've just said there. So what led you to apply for the Oliver Barclay lectureship?
Well, I think because Christians in Science did really help me in my journey, and I had a bursary for Faraday Institute summer school, and that really helped as well. And ever since becoming involved, I wanted to see what I had to contribute to the conversation, and having always loved quantum mechanics, I thought, okay, well, maybe I can say something about quantum mechanics. And yeah, I just wanted to have the chance to make my voice heard on this, and get feedback from all the questions we're having now. And I just wanted to get my ideas out there and see what people have to say in response.
Brilliant, excellent reason. Yeah. So what comes next for you? Because you had your paper in Zygon on theological aspects of quantum mechanics. You've got your research at your work. What's next for Anna?
Well, I really enjoy my work. There's a lot to be done in quantum computing, so I'm gonna keep my head down, keep on researching, and if any new theological ideas pop up, then I'll look into those as well. But research is like trying to drink the ocean dry. I mean, there's always more to be done. So yeah.
So just as a final question, do you have any recommended resources for people who might want to look more into both the quantum world, but also kind of the theological side of it as well?
So I've been thinking about this. I'm really bad at recommending resources because I did the traditional route of doing a physics degree and then a PhD and everything. So if you're young, go and do a physics degree would be my advice. In terms of general quantum resources, the website that had the little animation that I showed in the talk, that's got lots of animations about different quantum phenomena, and I find it really helpful for explaining difficult concepts in a nice way. If you're interested in quantum computing, there's a IBM Quantum Experience website, which has a lot of resources. When it comes to quantum mechanics and theology, I mean, I know you hosted a talk by Professor
Mark Harris.
Mark Harris, yeah. But I'm still kind of getting into the whole wider area of quantum mechanics and theology, so I'm not yet in a place to recommend things yet. But for those watching, that was a lecture a couple months ago, I think now, that the Manchester CIS group hosted. You can find that lecture by Professor Mark Harris on the YouTube channel of CIS. So yeah, that might be a good place for people who want to start digging into it a little bit more. But yes, I think that is all our questions for now for Anna. So thank you very much again, Anna, for your talk. Congratulations on the lectureship this year. We'll look forward to hearing more from you in the future on these topics. For the rest of us, we will be back at 3 o'clock for our next talk, which will be from Peter Phillips, who will be speaking on the digital church in a post-COVID world. So that's at 3 o'clock. Just a reminder about the feedback form. If you want to start taking a look at that in between now and the next talk, that will be great as well. Otherwise, we'll see you at 3 o'clock. Thank you again, Anna, and thank you to all of you for your questions. Thank you very much.